Okay. Yeah. Today, I'm going to talk about something about the Earth's core, and this is one of the outcomes of my ERC project, which ended a few years ago. And that ERC project started after I came to this country, 2013. The project started 2015 or 16. And then lots of people helped me set up my experiment laboratory at Edinburgh, and also helped me do some synchrotron experiment at synchrotrons, European synchrotrons, such as DESI in Germany and ESRM in France. So I really appreciate all these people named here. Okay, so there are lots of unsolved mysteries or problems regarding Earth's core. And many of them are somehow related to the composition. So the biggest problem to me is its chemical composition, the bulk composition. So from meteorites and seismic data, we are sure that the Earth's core is mainly composed of iron alloy plus few % of nickel. But there must be something else. This X is today's focus. Okay, this diagram is the starting diagram for the discussion. This is the density versus pressure diagram. The outer core spans 135 gigapascals to 330 gigapascals GPa, and beyond that pressure is solid inner core. This gray curve is seismologically constrained density profile. This is PREM. So this is one-dimensional averaged value. So you can assume this is the observation. This is the observed Earth's core density. And I plotted pure iron density for liquid by red and for solid by black at 6,500 Kelvin, which is close to the core temperature. And from this diagram, we can see that the Earth's core is less dense than pure iron. So the density difference, so-called density deficit, is 7% for the outer core and 4% for the inner core. So light elements, so there must be some light elements which reduce the density of iron alloy in the Earth's core. And this type of calculation was first done by Francis Birch in 1952, 70 years ago. And I'm just refining the density deficit value. So the first proposed value was between 10 and 20%, and now it's 7% for the outer core. The major candidates for the light element in the core is sulfur, silicon, oxygen, carbon, and or hydrogen. These are basically based on the cosmochemical abundances. Because the Earth's core is so large, so in order to reduce its density by 7%, so those light elements in the core must be abundant in the universe. So these 5 elements are the major candidates. There are lots of implications if you can identify the kind and the amount of light element in the core. And here I picked just one of them. So it's about the core formation process, how the Earth was formed. The Earth was formed by accreting meteorites 4.56 billion years ago. And here are 2 extreme end member scenarios. One is equilibrium model. The other one is disequilibrium model. So equilibrium model, this is kind of conventional picture of the core formation process. During accretion stage, the surface of the Earth was subjected to extensive melting. And then we had magma ocean here. And the depth of the magma ocean is uncertain, but at some point, we have solidified mantle here, this green. So this is the bottom of the magma ocean. And this bottom of the magma ocean, the iron pond should have developed. Okay? The melting point of silicate for the magma ocean is higher than the melting point of alloy. So within the magma ocean, it is expected that liquid iron should have been there. And at some point, this pond is getting unstable when it's growing up, and then it started descending to form the protocore of the Earth. And this bottom of the magma ocean is the place where the equilibrium element partitioning should have happened. Okay? And then the element from the magma ocean, namely silicon and oxygen, should have partitioned into the core melt here. And then silicon and oxygen are the resulting light element in the current core, if this scenario is true. So equilibrium model should result in silicon and oxygen as major light elements in the core. The another idea is disequilibrium model. Okay? So in this scenario, the differentiated bodies, okay, the differentiated core of this incoming body directly merges with the proto core of the Earth. In this case, there is not much time for the core, the iron alloy, to interact with the magma silicate component. So in this case, silicon and oxygen should have not partitioned into the core melt. And if there is light element in the core, that must be sulfur or carbon as the major light elements. So this scenario, this cartoon was taken from Ruby et al. 2011, but they are not suggesting this is the major scenario. So they suggested the earlier stage should be equilibrium process, and then later stage, this disequilibrium process might have happened. Okay? I'm just borrowing their cartoon for this presentation. So these two are extreme end member. So the reality, the truth might be somewhere between the two, but this clearly defines the importance of identification of light element in the core. Okay, so if it's silicon or oxygen, then the core formation process should have been under relatively equilibrium conditions. With that implication in mind, and people studied properties of iron light element bearing systems. Okay? So this is a summary diagram compiled by Hirase et al. 2013. The vertical axis is the number of published articles in favor of each light element, and the horizontal axis is the year. Okay? So here's 1950, and here's 2010. And the first proposition of light element in the core was, as I said, 1952 here, then the competition started. So looking at here, current 2010, the currently leading element is sulfur, followed by silicon and oxygen, and carbon and hydrogen are less popular. Yeah. So many people prefer sulfur in the core, but as you know, the scientific truth has nothing to do with democracy. And one caveat here is this may reflect the experimental difficulty. Okay? Experiment with sulfur, silicon, and oxygen are relatively easier compared to carbon and hydrogen experiment. So this may reflect that technical issue. And more than 300 papers were published regarding light element in the core. But one thing was poorly studied, that is mixing properties. Okay? So we have iron melt and we have light element melt, and we mix them to form a core melt. And the mixing properties were poorly studied under high pressure so far. The conventional approach is assuming ideal mixing. These two liquids or more multi-component liquid mix ideally. Okay, that sounds reasonable, but someone needs to check it, needs to test it. So we need to use chemical thermodynamics to do this. This is the Gibbs free energy diagram. This is free energy versus chemical composition. So we have an end member A and end member B. Okay? And the chemical potential of pure phase for A is here, for B is here. And when you mix these two liquids, okay, and if liquid is stable, liquid solution is stable, the Gibbs free energy should be like this downward convex curve. Okay. And in order to calculate this free energy curve, for example, this red point at composition X, okay, and someone invented a very smart, remarkable idea, that is this A activity. So this dot can be calculated by linearly averaging this chemical potential and this chemical potential. This is the chemical potential of component A in the solution here, okay? And this is pure phase plus RT ln A. R is the gas constant, T is of temperature, and a natural logarithm of activity. Okay, so the chemical thermodynamics, I mean, trying to constrain the mixing property, it's all about how we model the pressure effect of activity. Okay? So activity was invented, the concept of activity was proposed by Gilbert Lewis, who was a professor at the chemistry department, UC Berkeley. And he published this paper in 1907. And then following years, he published a very seminal, influential book that is Thermodynamics, the Free Energy of Chemical Substances in 1923. So this year is the 100th anniversary of the publication of this book. And in every seminar, in every talk, I'm showing this this picture. This is the copy that I have to celebrate this 100th year anniversary. And our approach to constrain the mixing property is two steps. One is the high pressure experiment, and then thermodynamic modeling based on that experimental data. So we use diamond anvil cell and using a pair of single crystal diamonds. So this is the top flat surface is so-called a cullet, and we place sample here and squeezing sample between the two diamonds and applying very high pressure. And this is the diamond anvil cell, okay? This metallic body. So you can see one diamond is sitting here and another diamond is sitting in this cylinder side. So this is a piston and cylinder structure. And combining this piston, assembling this piston and cylinder and mechanically screwing the cell, then you can generate very high pressure. Okay. And then thermodynamic modeling is, I'm trying to model the eutectic melting relationship, which I'll explain later. To construct the thermodynamic modeling, what are needed? So we need two pieces of information. One is the phase diagram, phase relations, and equation of state of phases. Okay. If you're not familiar with the word equation of state, this is about the pressure temperature effect on the volume. So namely the density. And the equation that we are using is very conventional. This is the Gibbs free energy as a function of pressure and temperature. This is obtained by this 1 bar high temperature term. This includes entropy of formation from the element and heat capacity, isobaric heat capacity, and this is standard entropy. And this 1 bar high temperature term are already available. If you go to the library, if you open up the meteorology database, you can find all these needed data. Okay, because of the requirement for the steel industry, the iron alloy materials are already well investigated at 1 bar. The high pressure effect is calculated using this term. This is the volume integration with pressure from reference pressure to the pressure of interest. And this is calculated from the equation of state. And equation of state that we are using is here. And this is bulk modulus. V naught is the reference volume, and the K prime is the pressure derivative of the bulk modulus. Now, again, if you are not really familiar with equation of state, this is just describing pressure and the temperature effect on density. And thermal expansivity term, this is a high temperature term, is calculated as a function of compression. Okay, so let me summarize the ion database first. This is the stability diagram for ion. This is temperature versus pressure diagram. So here's 1 bar 300 Kelvin, and this is the inner core boundary pressure 330 GPa. This is the outer core inner core boundary. Okay. The major phases that we needed to constrain are FCC structure, HCP structure, and liquid. Okay. This paper was published in 2014, and at that time, not well-constrained parameters are shown by green. So for the FCC phase, PVT equation of state was not really constrained at that time. And for HCP phase, enthalpy and entropy are not well constrained because this is a high pressure phase and there is no 1 bar data. And for the liquid, PVT equation of state was least constrained parameters. So we constrained these parameters by reproducing the phase boundaries constrained by diamond cell experiment. Okay, so these triangle experiments are on the FCC HCP boundary, and these circles are on the melting point of iron. So by calculating the free energy change, okay, to reproduce these experimental data, we fitted the PVT equation of state for the liquid. Okay. And these red curves are calculated results. And according to this, the melting point of iron at the inner core boundary is 6,300 Kelvin. And that's how we constrained the equation of state for the liquid in order to discuss the composition of the outer core. And this needs to be tested, okay? And recent years, some groups tested my equation of state, okay? So this is the result of first principles calculations. So this is computer simulation based on the quantum mechanics and the statistical mechanics. They can calculate the energy of a material without any information from experiment. This is density versus pressure diagram, and along the temperature profile in one of those exoplanets. Okay. If you have a good eye, you can see this black line is here. And also, if you have a good eye, you can see green line is just behind this black line. Okay. The black line is their first principles result, this study, and green line is my equation of state. So Komabayashi 2014 here. So this shows perfect agreement up to pay attention to the unit. This is not gigapascal, this is terapascals. So up to 2000 gigapascals and 10,000 Kelvin. Okay, and I'm not showing another data, but another group at UCL did similar first principles calculation and then confirmed that my equation of state is valid up to at least within the outer core pressure temperature range. Okay. So here's a bit more about thermodynamics. So this is the Gibbs free energy versus pressure and the temperature. So from the second law of thermodynamics, any material in the universe must take this form of Gibbs free energy surface. So this form is, this is mathematical information, namely the free energy is increasing with pressure and it is upward convex. And with increasing temperature, it is decreasing. And again, it's upward convex. Okay? So any material must take this form. Okay? This convexity is very important. Okay? So the slope, if you differentiate the Gibbs free energy with respect to pressure, for example, so that is expressed as this slope. The slope here represents the volume, molar volume. Okay? So at low pressure, the slope is larger, namely the volume is larger. And upon compression, then the slope is getting leveling off, namely the volume is smaller, smaller, smaller. Okay? And you can do the same exercise with temperature. The slope gives you minus entropy. So the slope represents the magnitude of entropy. Okay? So at low temperature, the slope is smaller. And with increasing temperature, the slope is getting larger, larger. So the entropy is getting larger with increasing temperature. Okay. So once you have established the Gibbs free energy surface properly, like this, then you can derive volume and entropy at any PT condition, consistently. And if you differentiate entropy and the volume again with P or T, then you can derive isobaric heat capacity, thermal expansivity, and bulk modulus. And isochoric heat capacity can be calculated from isobaric heat capacity and these parameters. And adiabatic bulk modulus can be calculated from these parameters. And all these are consistently derived from the Gibbs free energy. And for the discussion today, one of the important parameters is P-wave velocity for the liquid. That is adiabatic bulk modulus divided by the density. And these two parameters are calculated from the Gibbs free energy. So establishing the thermodynamic model is not about reproducing phase diagram, okay? But also we can derive all these important parameters consistently. And then we calculated ion density and the P-wave velocities over the outer core depth. This is velocity over density and depth diagram. The outer core depth, roughly saying, spans from 3,000 kilometer to 5,000 kilometer. So this blue curve is my equation of state. And this dashed gray curve is another liquid ion property profiles calculated by a group at Caltech. And this black thin line is Prem again. So the blue curve and the dashed gray curve are very consistent. And that shows the density deficit is 7% for the outer core. And here's new information, that is the P-wave velocity. The P-wave velocity of pure ion is slower than the Earth's outer core. So the requirement for the light element in the core should increase P-wave velocity and reduce the density. So this is a reference diagram. And then I'm now moving on to one of the binary systems, iron sulfur. So this is one of the most recent publications from my group, and this was led by my former PhD student, Sam Thompson. So when he started his project, this is temperature pressure diagram showing the stability relations. These gray curves are ion phase relation. And previously, people constrained ion Fe3s eutectic point, eutectic temperature. Okay? So Fe3s becomes stable above at 20 GPa. Okay? So the people studied its eutectic relationship above 20 GPa, and they constrained the melting point, eutectic point. Okay? And at that time, no data was published, no data was available about the Fe3s melting point. So some constrained this by doing diamond cell experiment. The solid symbols are the places where we observed solid Fe3s, and open symbols are the PT conditions where we confirmed the melting happened. Okay. And Fe3s melting point is, of course, higher than Fe3s eutectic point. Okay, and this is showing you how we constrain the melting temperature, because identification of melting in the diamond cell experiment is very, very critically important. Okay, so this is a close-up of the sample chamber of diamond anvil. Okay, so here we have a sample. The sample is this light gray disk sandwiched by pressure medium, this dark gray material. Okay, so this sample needs to be isolated from diamond because diamond is a very good thermal conductor. If it's in directly contact with diamond, you can't really heat the sample. And after doing high pressure temperature experiment, we recover the sample by opening up the cell and then put that into a focused ion beam machine. And then using gallium beam, we can mill the sample, and then we can have a look at the cross section of the sample. The starting material was a disc. Okay, so if you look at the cross section, that has to be like this plate shaped. So we can see here is a non-melted region, here's a non-melted region, and in between is a molten texture here. And the heating was made by laser heating. So we introduced class 4 laser through diamond anvil to heat the sample. Okay, so in this case, from below, we introduced the laser to heat the sample. So this is the heated area, and actually laser heating produces large temperature gradient. So this is the heated area, and this is somehow heated but lower temperature. And we collect information about the temperature profile like this. So this is temperature versus distance from the center. And comparing this SEM image and this profile, then you can constrain the melting point here happens at 2700 Kelvin. And this is the data for the highest pressure point, 75 gigapascals here. Okay. And we do same thing for other data point to constrain the melting point. Okay. And then we did exactly the same thing as we did for IM thermodynamic modeling. So to reproduce this Fe3S melting point, we adjusted the equation of state parameters for liquid Fe3S. And then this is the summary table. So we constrain the equation of state parameters for different liquids. So this liquid ion, liquid FeO, FeSi, and then this is a newly added phase. This is the liquid Fe3S. Okay, now we are in a position to calculate eutectic relationship. So to calculate this kind of diagram, we need end member melting point and end member melting entropy. This is entropy jump at the melting. And we already constrained these two. So we know everything about ion. We know everything about Fe3S side. Okay? So only thing we need is a mixing parameter to calculate this liquidus curves and also this eutectic point. So to calculate this liquidus curve, this is the equation we use. This is left-hand side is the activity of ion in liquid, and right-hand side is entropy of fusion divided by the gas constant, melting point of end member, and the temperature of interest. So this is a univariant reaction between activity and the temperature. And activity is a thermodynamically corrected composition. So activity equals activity coefficient gamma times composition. Okay? So roughly saying this is composition versus temperature relationship. Okay, so before getting to high pressure data, let me introduce you to the 1-bar data. Okay? This is from metallurgy database. This is temperature versus sulfur content, and liquidus curve shows this sigmoidal shape, this complicated sigmoidal shape curve. This is because the Fe sulfur mixing property shows negatively non-ideal behavior. If iron and sulfur shows ideal mixing, it should be like this black dashed curve. But to reproduce these experimental data, so FES mixing, it should be like this. This is negatively, largely non-ideal mixing behavior. The question here is how this evolves with increasing pressure. Okay, so how we did this is to reproduce experimentally constrained eutectic temperatures, okay, which I showed you 5 minutes ago. Okay. To reproduce this eutectic point, we adjusted the gamma coefficient at each pressure and then fitted it to a polynomial function. Okay. This is RT and gamma. This is a capital letter, but same. This is activity coefficient gamma for ion and Fe3S, and they are function of mole fraction and interaction parameter L. Okay. And L is a function of pressure, and we fitted this function to reproduce these experimental data. And this is a resulted L parameter as a function of P. And then we calculated eutectic composition. This is sulfur content versus pressure. And experimental constraints are plotted here. And it shows kind of a linear decreasing trend. And our thermodynamic calculation shows a kind of quadratic behavior. Okay, it's getting leveling off. But considering the uncertainty in experiment, so this curve is fairly consistent up to 200 GPa. And this highest point is something we are not reproducing by thermodynamic calculation. But this assures overall consistency, eutectic composition, and eutectic melting point. And this is the Gibbs energy diagram. This is Gibbs energy versus composition. And iron and Fe3s here is Fe 0.75, Fe 0.25. This is Fe3s. And if these two forms ideal mixing, should be like this. But in order to reproduce eutectic point, then the Gibbs energy must show a little bit negative non-ideal behavior. Okay. And this is at the top of the outer core. This is at the bottom of the outer core. So throughout the outer core, the FeS mixing should be non-ideal. And previously, we did exactly the same thing to iron oxygen system, iron silicon system. And in these systems, the mixing can be ideal mixing. Okay? And Fe sulfur system shows non-ideal. And then I'm now moving on to the discussion part. We are going to calculate expected core properties for a given composition. The first property we need to calculate is the temperature profile of the outer core. This is temperature pressure diagram. And here is the core mantle boundary pressure. This is the inner core boundary pressure. So this is outer core region. So the outer core is liquid and inner core is solid. That means the outer core is crystallizing to form the inner core. So the temperature at the inner core boundary here represents the crystallizing point of the outer core. So if you know the crystallizing point, then that can constrain the inner core boundary temperature. And in the case of a pure iron, the crystallizing point is here. Okay? And then we can calculate the temperature profile according to this equation. This is the Gruneisen parameter, and this gamma is not the activity coefficient. Sorry, this is confusing, but this is Gruneisen parameter. Okay. And this represents the temperature change according to the density change at an isentropic condition. So this produces the isentropic temperature profile. And thermodynamically, we can calculate this using thermal expansivity, bulk modulus, volume, and isochloric heat capacity. All these can be derived from the Gibbs flow energy. So iron temperature profile is here, blue one. And if you add silicon for weight %, the starting point doesn't change much, but the profile is getting a bit steeper. And if you add oxygen, 6 weight %, then the starting point is drastically reduced because of the eutectic relationship. Okay? This is a liquidus point for this composition. And then the slope is also very different from pure iron's slope, okay? Because the material's properties are different to calculate this Gruneisen parameter. Okay? So this is one of the advantages of constructing a thermodynamic model. The conventional discussion is when people constrain something new, like new melting point, new equation of state, and then when they discuss the outer core property, they use the Gruneisen parameter for pure iron published by someone. But that's not the right thing to do because the Gruneisen parameter strongly depends on the chemical composition. Okay, then we calculated the iron sulfur liquid property along that temperature profile. So in this diagram, the pure iron is this gray dashed curve here, okay? And these purple dots are prime data point. So first we calculated 16 weight% sulfur bearing system. This is Fe3S composition, shown as this dashed red curve. So in terms of density and the P-wave velocity both match the prem, okay, along the temperature profile. This sounds good, but we have to match the inner core prem profile as well. So this is the eutectic diagram for 330 gigapascals. This corresponds to the inner core boundary pressure. And then Fe3S is here. So if you crystallize Fe3S outer core, the crystallizing phase is Fe2S. Okay? So Fe3S solid phase is no longer stable at this pressure, and instead Fe2S is stable. And Fe2S is outside this horizontal line. I'm sorry, it should be like here. Okay? So if you crystallize Fe3S composition, then the crystallizing phase is Fe2S. And then we estimated the possible density range for the Fe2S. Okay? And that's comparable to the Fe3S outer core density. Okay? This is not nice in order to, when we try to explain this inner core density, okay, the crystallizing phase must be much denser than Fe2S. So we tried another composition. Okay, so this case we tried a 6 weight% sulfur bearing ion system in order to produce dense ion phase here. Okay, and the result is this solid red curve here. Okay, and this case the density reduction is not enough, and the velocity increase is not enough. So based on this case study, we can say that iron sulfur binary system cannot account for the Earth's core. And then we did previously the same argument discussion for the iron oxygen system. So blue is pure iron and red is 6 weight% bearing oxygen system. So density is reduced, okay, but P-wave velocity is reduced as well. This is not nice, okay, because that has to be increased. So iron oxygen binary system is also rejected. And this is iron silicon and iron silicon oxygen system. So jumping to the conclusion, so this red curve here, this is 6 weight% silicon, 1 weight% oxygen bearing system. And this composition perfectly matches the prem, both density and P-wave velocity. And then question is, what about the inner core phase, crystallizing phase? Okay, so that is here, this star symbol is the crystallizing phase density. Okay, this is still not enough to reproduce the inner core density, but this works better than the iron sulfur system. Okay, at least this can produce the difference between the outer core and the inner core. So far this is the conclusion, and this is summary slide. I'm sorry, this is not the last slide of this presentation. So let me just read out the third conclusion. None of the sulfur, silicon, and oxygen alone can match the prime profiles, but the iron, silicon, oxygen ternary system works better. So this suggests that the core formation process should have been under relatively equilibrium conditions. And then let me briefly talk about Mars, Martian core. Okay. So NASA launched so-called InSight mission, and they deployed seismometers on the surface of the Mars, and they got the first data published in 2021. Okay. And they only got mean core density and mean core radius, and I'm going to show you the data in the next slide. But this is very remarkable step, because now we can study the Martian interior like we do the Earth's interior. This is their data. This is the mean core density on the y-axis, and on the x-axis, this is the core radius. Okay? And these dots are the statistical data. Okay? And they can, at the moment, only constrain the mean core density with this large uncertainty, and the core radius is accordingly showing this large uncertainty. But the authors started preliminary analysis, what kind of composition can match this density. And the geochemists prefer iron 5-weight% oxygen and sulfur system. So this is iron sulfur oxygen system. Okay? So how you read this band is, so they fix iron at 5-weight% oxygen and changing sulfur content. Okay, so from 15-weight% to 30%. Okay, and then accordingly the density is calculated. Okay, so this band showing the change in the sulfur content. Okay. So the conclusion is iron sulfur oxygen system can match the major part of these plots. Okay? But if you like to, but the point is sulfur content, for example, to match the mean core density here, then the required sulfur content is 22 something, 22, 23. Okay, which is much larger than the geochemically inferred value that is between 15 and 19. So if we take sulfur value from cosmochemically constrained value here, then you have to put something else like carbon or hydrogen to further reduce the density. But again, so Fe sulfur oxygen system can match the major part of this data if you ignore the constraints in terms of sulfur content. Okay? So looking at this data, so they used my equation of state for pure iron and oxygen system. Okay? So at this time, 2021, Sam Thompson's paper was not published. And then if we calculate this iron sulfur 5-weight% oxygen, this band, with our newly determined iron sulfur equation of state, that is here. Okay, so this produces much denser profile because our iron sulfur equation of state produces much denser than the model used in producing in this paper producing this band. So probably we are complicating the situation because definitely we need to put additional light elements such as hydrogen or carbon. But this is the way we study the deep planetary interior. And thank you very much. That's everything.
This is probably a naive question, but where is the sulfur that's like for each other
So the major conclusion here is iron sulfur binary system doesn't work, but you can put small amount of sulfur and together with other light elements. Okay? So that's my hypothesis. Probably, and if it's together with silicon and oxygen, then 1% or 2-weight% sulfur is fine in the core. Yeah. Yeah, so according to the equilibrium experiment, like sulfur partitioning experiment between core metal and the mantle silicate in the magma ocean, so the 2-weight% sulfur can be possible in the core. So that's geochemistry argument. So the 2-weight% sulfur is fine. Okay. The inner core and outer core should be not very, but should be different in composition, because when it's pure iron, crystallization changes density, produces density, difference, and that is up to 2% at this pressure, and this prime density jump is 4% or something. So the 2% should come from the compositional difference. Yeah.
So, first question, you're comparing everything to Prem.
Yeah.
Prem was a marvelous model, but it's 50 years old. And particularly, I mean, I'm quite willing to believe it's seismic velocities, but the density, normal modes have set, has density really not changed our estimates for density from Prem?
So talking about the outer core, the different model produces quite similar density profile, like AK135. And it's well mixed. Hydrostaticity is guaranteed. So density of the outer core is kind of well constrained.
I mean, the global models are kind of similar-ish, but the constraint is coming from, particularly from normal modes, and that reserved data has changed over time. So we do think that, I don't know, I mean, I know that people have argued for slightly different densities as they go through how much the difference it would make.
Okay.
I mean, Prem is a good thing to fit, sure. As I say, it's been around quite a long time. So anyway, next question is, when we look at the core, we talk about the iron, we don't talk about the iron core, we talk about the iron nickel core. How sure are we that putting nickel in there makes no difference?
That can make a difference, actually.
How much?
I have no idea at the moment. Yeah, that depends on the combination, what kind of light element you put together. And
it would be about, I mean, it's a reasonable level percentage of the composition. It's something like,
yeah, 5 to 10 weight percent. Yeah.
So there's another. I mean, it's a bit of a problem. I mean, I love you mentioned Francis Birch's 1952 paper, his lovely quote that at high pressure language core is pure iron, and at low pressure, but really at high pressure, it's an uncertain mixture of all the elements. So you're already showing with a ternary that, you know, you put things together, things change, but nickel is, let's say, 10%.
Yeah.
So it would be good to be certain that that's not actually impacting on, if we're trying to decide between different kind of members, that we don't put in nickel and doesn't reorder the.
Yeah, because nickel and iron are kind of neighbors in the periodic table. And
that's true. But I'd rather an experimental or even a calculation of it to demonstrate it rather than, oh, they're neighbors in the periodic table. Is it possible to do that experiment with some nickel?
Yeah, well, I did a couple of experiments in the iron nickel system, iron silicon nickel system, and in some cases, the result is just as expected, and some cases a bit of unexpected. And at the moment, I can't give you the consistent picture.
So when you say unexpected, how unexpected?
For example, the phase relation is very different from the pure iron light element.
To make a difference in some of the results you're hoping.
Well, at the moment, nickel just changes the stability of structures, stability relations, and I didn't look into the density and the PV velocity.
Yeah, you showed me you showed the diagram where you fit your relationship to the data.
Yeah. Which composition?
That's the one. That's one. So yes, your model kind of generally fits the data, but if I were to take the red curve away, I'd plot a straight line through that. Would that be a possible solution?
No.
Why?
Because this eutectic composition is moving to the sulfur depleted area. So that means, so this composition is moving that side. Okay. So if it's getting closer, then you need to have a very large difference in the chemical potential of a pure end member. Okay. And if it goes further close to the pure iron, then you have to have even larger difference in the chemical potential. That's not happening because the pressure dependence of the chemical potential is from molar volume, and they are kind of similar under core pressure. So you can't make further difference with increasing pressure. So when it approaches the sulfur iron side, then this should be leveling off.
So the theory is very convincing, but nonetheless, if I look at those data, what I teach a course in data modeling, and I always tell my students to block the residual. And you've got the residual, it's going to be another sign.
For this particular case, the chemical composition analysis in the diamond zone is still challenging. It has very large uncertainty because the grain is so small. So that's why I fitted to the eutectic temperature, which is relatively well constrained because temperature measurement is kind of sure. So we fitted to the temperature information and then calculate the composition rather than fitted to composition.
So if you get composition, you make it look, I mean, not the correct thing to do, but can you at least, if you just get composition, make it. And
again, no, as I said, the chemical potential relationship cannot make a straight line.
That little round circle at the bottom, I mean, the rest of it that accentuates probably, but that little round circle would be nice to get some more data on that.
Yes.
Sorry, John, I think you had a question.
Yes, so stepping back from the details. I mean, at the start, you showed some kind of planetismal crashing into the Earth, making the core violate this equilibrium.
The first one?
Now, and then I think you kind of
this one
stepped aside from that. But I'm no expert on this, but it seems to be widely accepted that a small planetesimal crashed into the Earth and formed the Moon. So so actually, if we accept that's part of the Earth story, where does you've been advocating equilibrium, but that would have induced some fairly violent disequilibrium. I don't know where it fits in the story, the collision of this planet with the Earth. Am I right that it is generally accepted that the Moon was formed by a collision, didn't it?
Yes, I think so. Yeah.
Yes.
I haven't studied myself, but yeah.
I mean, maybe that happened. I honestly, I literally have no idea how about these early hundreds of millions of years of the Earth. I don't know whether that was before the magma ocean or.
Probably during magma ocean period. Yeah. So one of the recent papers was in Nature Geoscience. Yeah, led by Japanese and Shun Karato. And yeah, so they simulated the collision of an incoming body collided with the magma ocean. And that magma ocean collision can explain all these geochemical natures.
So you're advocating that the liquid outer core, it's the essence of your model is the liquid outer core has got silicon and oxygen as the light elements. Yeah.
Mm-hmm.
So, but again, I'm sort of thinking about the bigger picture. So somehow a liquid with iron, silicon, and oxygen has kind of made its way down into the liquid outer core. I mean, I wonder what scope there is. People must have modeled the interactions of those chemicals on the way down through the solid, dominantly silicate mantle.
Mm-hmm.
Is there any leverage? Is there any insight you can get from such considerations?
Talking about interaction with solid mantle.
Well, yes, you must have interacted somehow. In fact, sorry to add to my question without making it focus. There must be a lot of redox going on.
Mm-hmm.
I mean, silicon is mainly Si4+.
Yeah. Yeah.
So was there always some silicon and it found its way down, or has the silicon been reduced on the way down by some process? I can't imagine that.
Well, silicon oxygen partitioning, it depends on oxygen fugacity and also depends on pressure. So if it's shallow level, two elements cannot be simultaneously partitioned into the core. So if the body is small, then silicon or oxygen, so either of them can be dominantly partitioned in the core. And with increasing pressure, these two can be mutually fine with each other. So yeah, that depends on the core formation scenario and how small steps you make in your simulation.
The inner core, what do you think? Maybe I missed it, but what's actually the inner core?
Oh, as I said, my hypothesis is if you put 2 weight percent sulfur. So looking at this diagram, so this is 6 weight percent sulfur bearing iron, and this doesn't reduce density very much. So and as I said, 2% sulfur is fine. You can put into the core, and the 2% doesn't really affect for the density relationship. But if you put 2 weight percent sulfur, that can be, so 2 weight percent sulfur can go into the crystallizing phase as well. So that changes the density of this star. So I'm expecting this could be increased by this much by adding sulfur. Yeah. Yeah. Thank you very much.